Hello and welcome to the Daily Space. My name is Annie Wilson, and most weekdays, the CosmoQuest team is here putting science into your brain. Today, however, is for Rocket Roundup. Let's get to it, shall we? For our first launch this week, on May 18th at 17:31 UTC, an Atlas V 421 launched the SBIRS GEO-5 mission into geostationary transfer orbit from Slick 41 at Cape Canaveral Space Force Station in Florida. The 421 in the rocket name means that the Atlas V has a 4-meter payload fairing on top of its Centaur upper stage, 2 solid boosters on the first stage, and a single RL-10 engine on the second stage Centaur. SBIRS stands for Space-Based Infrared System and is the current system used by the U.S. government to detect intercontinental ballistic missile launches. It replaces the Defense Support Program, which launched in the 1970s. SBIRS uses 2 different sensors, a scanning sensor and a starting sensor. The scanning sensor is used to provide quicker revisit time over wide areas, and the starting sensor is used to look at smaller areas for longer times. Let's watch the launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, Atlas ignition, 2, 1, and liftoff. Liftoff, the United Launch Alliance Atlas V rocket with the 5th Space-Based Infrared System satellite for the United States Space Force.
Next up, on May 19th at 4:10 UTC, a Long March 4 Bravo launched the He-Yang to Delta satellite into orbit from the Qiuquan Satellite Launch Center in northern China. The purpose of the satellite is to monitor the dynamic ocean environment with microwave sensors to detect sea surface wind, height, and temperature. It does this with an altimeter, which literally measures altitude, and a scatterometer, a specialized type of active radar optimized to determine the direction of the wind over large bodies of water. Both instruments work by sending out radar pulses to the ocean and recording the reflections. The altitude, wind speed, and direction are a function of the returned energy. A rough ocean surface returns a stronger signal because the waves reflect more of the energy back towards the scatterometer antenna. A smooth ocean surface returns a weaker signal because less of the energy is reflected. And of course, there's a launch video. For our last launch of the week, we have another notable space flight. On May 22nd, the Virgin SpaceShip Unity suborbital plane made its 20th flight. This was the first successful powered flight of the vehicle from its new base at Spaceport America in New Mexico. The major goals of the flight were to test the upgraded horizontal stabilizer, collect data for their FAA license, and do a bit of science while they were at it. The carrier aircraft Virgin Mothership Eve took off at 14:34 UTC with the Unity attached and began an hour-long climb to release altitude. At 15:26 UTC, the Unity was released to begin its rocket-powered climb to an altitude of 89.2 kilometers. The motor burned for 60 seconds before shutting down, which allowed the vehicle to coast. Apogee was reached 6 minutes later at 15:32 UTC. After the motor shut off, the vehicle moved its tail fin into the feathered re-entry position. The Unity touched back down at Spaceport America at 15:43 UTC. Let's watch the flight.
3, 2, 1, release, release, release.
Fire.
Fire.
CJ Mac, we took test points Alpha and Bravo complete. You're going to space. Again.
Accompanying the two Virgin Galactic test pilots were two payloads from NASA. One of the payloads was APL-SRLV Environment Monitoring System, also known as ASEMS. Launched under NASA's Flight Opportunities Program, this simple, self-contained payload created by the Applied Physics Laboratory at Johns Hopkins University is intended to be rapidly deployed with commercial off-the-shelf electromagnetic field measurement devices for use on suborbital reusable launch vehicles. It weighs 5.5 kilograms, about 3 2-liter soda bottles, and contains a variety of electronics. The other NASA payload was COLLIDE, which stands for Collisions into Dust Experiment. According to NASA, this experiment is a modified version of the COLLIDE that was flown previously on 2 space shuttle missions. If you've ever played around with making your own craters by dropping balls into sand or flour, COLLIDE's experiment will be pretty familiar to you. COLLIDE will drop an impactor, a ball, into a tray filled with a fine-grained target material, like sand, and use a video camera to record the whole thing. The data collected will help scientists understand how dust, such as lunar soil, behaves in low-gravity environments. It will also be used to design equipment and science instruments on the moon for future crewed missions. After the break, we'll be back to talk about rocket fuel. Stay tuned. One of the many propellants you frequently hear me mention in different stories is hydrolox. Hydrolox is considered the most efficient rocket propellant combination ever, with an average specific impulse of around 450 seconds. Average specific impulse is basically how much energy the fuel has per 1 unit of propellant. For comparison, Kerolox engines use rocket propellant 1, a form of kerosene, and liquid oxygen. They have an average specific impulse in the mid-300s. The Merlin 1 Delta on the SpaceX's Falcon 9 uses an RP-1 and liquid oxygen combination. What this means is that you can get more velocity from the same amount of hydrolox propellant because hydrogen molecules are very small and easy to accelerate quickly out of the throat of your rocket engine. This all sounds great, right? Well, it's more complicated than that. This is rocket science after all. The thing that makes hydrogen a good propellant, its small molecular size, also makes it really difficult to store. It simply doesn't want to stay where you put it and will leak super easily. The super cold hydrogen also is problematic to store in fuel tanks for long periods of time. Keep those tanks filled for too long and the walls will become brittle and crack. This isn't good for something that needs to survive the mechanical and thermal stresses of passing through the atmosphere at a high speed, like a rocket going into space. Special care is taken to load and empty liquid hydrogen from a rocket tank a limited number of times. The Space Shuttle external tank was only capable of 13 fill and drain cycles, and the Space Launch System core stage is capable of 22. This seems like a lot until you realize how much processing the SLS goes through that involves tanking and detanking. Remember, in early 2021, the SLS core stage was on the B2 test stand at Marshall doing its green run full demonstration hold down fire test. That test ended 67 seconds into a planned 480 seconds. In post-test communication, NASA implied that the 67-second burn would just have to suffice because the core stage could only be filled 9 times. And it had already been filled 3 times in previous testing. There were no more spare cycles left. The remaining cycles were reserved for further propellant testing at the launch pad and for the launch itself. Later, NASA confirmed that a second green run needed to be completed, and in March 2021, a full 480-second green run was conducted with no apparent problems. Another disadvantage to using hydrogen is that it's not very dense. For such a small molecule, it takes up a whole lot of space. To hold rocket-usable amounts of it, you need a very, very large tank, which is exactly why the SLS core stage and the shuttle external tank are so large. And now you know. After the break, we'll be back with This Week in Space History and a look at the Skylab mission. This week in rocket history, we're looking back at the first crewed mission to USA's first space station, Skylab 1, or 2, depending on who you ask. The first crewed mission to Skylab was originally called Skylab 1 and then retroactively changed to Skylab 2. Some sources still call it Skylab 1. The Rocket Roundup team was highly annoyed with this, so to keep the confusion to a minimum, we'll refer to it as the first crewed Skylab mission. Anyways, Skylab, the space station, was, and this is wild. Just listen, this is wild. Skylab, the space station, was a converted Saturn V third stage, fitted out on the ground and launched on another Saturn V. The original plan was to launch Skylab as an active wet workshop where it would launch as the second stage of the much smaller Saturn I Bravo rocket and insert itself into orbit and be converted to a space station there. Yes, that means they were going to fill the second stage with fuel and some internal bits, launch it into space, drain the remaining fuel, and convert the now empty second stage to a space station on orbit. But after Apollo 18 through 20 were canceled, the concept switched to a dry workshop launched on one of the now spare Saturn V's. Skylab, the space station, was launched on May 14th, 1973, and suffered some damage on the way up. During launch, the station's micrometeoroid shield, which protects the pressurized space from impacts with debris, separated early. The errant shield took off one of the two solar arrays with it. This caused a lot of problems, most importantly, making the station too hot to enter safely, over 54 degrees Celsius or about 130 degrees Fahrenheit. All other aspects of the launch were normal. The Apollo telescope mount with its smaller solar panels were deployed, giving the station a small amount of power. This was clearly a major problem, and NASA set to work on a repair to be implemented by the first crewed mission a week later. This made that very first crewed mission to the space station a very critical one. In order to make the needed repairs, NASA first needed to know the extent of the damage. A highly classified National Reconnaissance Office Keyhole 8 Gambit 3 film camera reconnaissance satellite, yes, that's a spy satellite, was tasked with taking pictures of the damaged station to assist with the repair plan. The satellite was launched on May 16th. Skylab, the space station, was imaged on May 19th, and the photo was returned to the ground, along with pictures of targets in the Soviet Union, which was its primary mission, on May 20th. Following the rushed design and build of an expandable sunshade in 7 days, the crewed Skylab mission was launched on May 25th, 1973 at 1300 hours UTC. The three crew members were Pete Conrad as commander, Paul Weitz as command module pilot, and Joseph Kerwin as silence pilot. They launched in an Apollo command module carried to orbit on a two-stage Saturn I Bravo. Because of the low Earth orbit destination and the capability of the launch vehicle, the service module was loaded with much less fuel than it would have been for a lunar mission. The launch of the first crewed Skylab mission was nominal, and on its 5th orbit, it successfully rendezvoused with Skylab, the space station. Command Module pilot Weitz flew the Apollo around the station and inspected the damage before docking, which turned out to be very difficult. It took 8 attempts to achieve a hard dock. As soon as they docked with the space station, it was time to get to work. The crew attempted a spacewalk to free the stuck solar panel, with Weitz standing up in the Apollo and pulling on the debris that was keeping the solar panel stuck using a cable cutter on the end of a 3-meter pole. Meanwhile, Conrad flew the spacecraft. This first wild attempt was unfortunately unsuccessful. The crew boarded the station, and on the second day of flight, they absolutely had to do something about the temperature. Remember, it was over 54 degrees Celsius inside the station. So the sunshade was deployed by the astronauts from inside the station by using the science airlock in the Apollo telescope mount. Once the sunshade was finally deployed, the temperature in the module immediately dropped at a rate of 18 degrees Celsius or 64 degrees Fahrenheit per hour. It stabilized at a much more reasonable 23 degrees Celsius or 74 degrees Fahrenheit. With the interior now at a comfortable temperature, the next step was to free the solar panel. This was successfully completed on the second spacewalk of the mission on June 7th, which was conducted from an airlock on board Skylab, a Gemini spacecraft hatch built into the structure. This spacewalk was not without problems, however, as Kerwin and Conrad found that the actual station differed from the mock-up that they had trained on. And at the moment the solar panel was freed, the 2 astronauts were flung off of the structure by the force. They remained attached through their tethers, and the shaken astronauts were able to return to the inside of the station. The rest of the astronauts' 28 total days in space were much less eventful. On June 19th, Conrad and Weitz performed the 3rd and final spacewalk of the mission. This one was completely nominal. The 2 spacewalkers used handrails to move around and a pulley system to remove film canisters and space environment samples from around the module. They also cleaned the outside of one of the telescopes and performed percussive maintenance. Yes, they hit it with a hammer to reopen a stuck circuit breaker, preventing all of the power generated by the module from going to Skylab proper. Together, the crew performed around 392 hours of scientific experiments, including observing 2 major solar flares with the telescopes. They also conducted further investigations into the human body's reaction to weightlessness made possible by that vast converted fuel tank that formed Skylab's pressurized module. Some of the equipment included a rotating chair and a 0G treadmill to gauge the ability of a human body to do physical work in space. The Apollo capsule carrying the first astronauts to Skylab splashed down in the Pacific Ocean 1,320 kilometers west of San Diego, California at 1349 UTC on June 22, 1973. The USS Ticonderoga, an Essex-class aircraft carrier, handled the recovery. After the break, we'll round out the show with this week's Stats and Fact. Don't go away. To wrap things up, here's a running tally of a few spaceflight statistics for the current year. There are currently 6 toilets in space, 3 installed on the International Space Station, 1 on the Crew Dragon, 1 on the Soyuz, and 1 on the Chinese Space Station. There have been 45 total orbital launch attempts so far this year, including 2 failures. 1,046 satellites have been put into orbit from those launches. I keep track of orbital launches by where they launched from, also known as spaceport. Here's that breakdown. USA 19, China 14, Kazakhstan 4, Russia 3, New Zealand 3, French Guiana 1, India 1. And your random space fact for the week is that the smallest rocket to put something into orbit is Japan's SS-520, a converted sounding rocket created by adding a third stage to the S-520 two-stage sounding rocket. The SS-520 is 9.5 meters tall, half a meter in diameter, and weighs 2.6 metric tons. Although the first launch of the SS-520 failed, the second launch succeeded in putting the 3-kilogram Tricom-1 Romeo CubeSat into orbit on February 3rd, 2018 from Japan's Uchinori Space Center. This has been the Daily Space.